Okay, for people who are joining this live stream, we are here to talk about virtual machine implementation for blockchains in Wolfram Language. And unusually for, in fact, probably the first time in one of these live streams that I've done of our design meetings, I am not in my usual home location. I'm off in some random hotel room, as it happens, with a view of the Hudson River in New York City. I think it's the Hudson River. No, maybe it's the other side of New York. I don't even know. Some big river. Okay. So let's get started here. So the basic idea is to be able to take, for example, the messages that are on the blockchain. And so for example, let's say I bring up, let's say I do blockchain block data, and I look at, I'm just trying to understand what I'm able to do here. So I'm able to take this and I say, so we're dealing with, are we dealing with Bitcoin, or we're dealing with both Bitcoin and Ethereum here? Is that correct?
Depends on which base are you in. But the virtual machine right now is only for Ethereum.
Okay, fine. So, I mean, the Bitcoin virtual machine is simpler, right?
Well, I have to insist that no one refers to that as a Bitcoin virtual machine. I think we have to first decide what we are calling a virtual machine. If it's just software that runs bytecode, we could call the Bitcoin script a virtual machine, but that will mean that we have to call another type of things, like some libraries. They will be called also virtual machines.
Well, yeah, I mean, lots of things. Okay, so here, this is, so where is the, where's the script here? I mean, I just picked this random transaction. Where is the script? Input data, byte array, is that the script?
Yeah, the byte array.
Okay, so there's a decompiler that we're expecting that goes from that byte array to some symbolic representation. Is that correct?
Yeah, but if you go to the notebook, perhaps we can show you what's.
Although I just want to clarify that in Ethereum, in Bitcoin, there's, you know, if I look at the analogous thing, you know, let's pick this for Bitcoin. Let's see, I could probably just say, what do? I just say transaction. Is that correct?
Transaction list, and get a random transaction from there and change your blockchain base to Bitcoin. And do a random choice of that.
I can just say take 5 or something. Okay.
Just don't take the first one, because the first one is a coin-based transaction, which is a special transaction.
Don't take the first one? Well, let me take all of them.
It's listable. You can also use it as the first argument.
So the script byte array is what we're talking about here, right?
Yeah, it's easier to see the script string, to see the opcodes.
Okay, so that is something which has a sort of, what is that? Brackets all there. That's really weird.
That's a flag. So you're seeing their signature and a public key, and that's a flag that tells some opcode what to do.
But so, like, these might be pay to public hash or something. Is that right? I mean, how would I tell?
You're seeing the input script. You're referring to the output script. So if you go a little bit down to the output you have there you're seeing a pay to script hash type script. A pay to public key hash, probably around there too.
Okay, so this is a symbolic version. I mean, not a symbolic, but it's at least a string version of the script. Do we have a similar string version of the Ethereum scripts?
Not for transaction data.
Okay, but there is a string analog. There is, for Ethereum, there's a similar kind of string analog.
Yes, yes, there is.
Okay. Okay, well, it might be nice if we had that, if we had a script string for the Ethereum case too. Although clearly the symbolic version is what we really want. So with that intro, let's launch into what you're talking about here. Okay, so is this my notes here? Were these my notes up here? Yes.
Yes.
Okay. Okay, so then it's something where there's a virtual machine, there's a state representation of the virtual machine, and there's a specification of what opcode is being accessed in that virtual machine, and that operates on the state to give a new state, right? That's what I would expect the virtual machine basically to do.
Yes.
Okay, so let's take a look at what you're talking about here. Okay, takes code in human readable form, opcode, returns it in bytecode form. Okay, but so from bytecode, so this is something where I should be able to take that function, virtual machine from bytecode, and I should be able to say up here, I should be able to take, which one is it? That's the Ethereum blockchain, so I should be able to take that byte array, is that correct? Yes? No?
Yes.
Okay, let's just make, this is Bitcoin down here, and this is Ethereum up here. And that's my byte array, and I should be able to say virtual machine from bytecode. What on earth is that? That looks wrong.
Yeah, we still have to support that directly from the byte array. There are some examples already in the notebook that what is working right now.
Okay, all right. Okay, so.
But it will work that way, of course.
Okay, all right. Okay, but that's in principle what happens here.
So yes, yeah. So you have two set of functions here. The first ones are just code management, as we mentioned here, and then we have the how to initialize a session and evaluate what you want in a virtual machine.
Okay. By the way, the people on our live stream are asking about visualization of things like Merkle trees. I mean, that's sort of orthogonal to what we're talking about here, but I think, I mean, Christian, have you guys been working on stuff like that?
We did some experiments with transactions and visualizing that, but just have some draft for that.
I see. It'd be nice to have some functions, at least in the function repository, that do do visualizations. I mean, I guess I've seen these kind of mega skyscraper-like visualizations of blockchain activity, which are entertaining but not directly useful. But I would think that the Merkle tree thing could be useful.
Right, but that visualization you saw probably required a lot of time of rendering. So also when you are trying to make the tree of all the stuff like in real time, it will take a bit of time to make it. So
I mean, arguably, once we have our own servers fully up and running, which is very soon, I think, caching some. I mean, there is one big Merkle tree, isn't there? And I mean, if we just cache that tree, and we are able to, index into pieces of it, we will be able to produce those tree fragments.
Yeah, we can come up with a way to have something specific for that.
Fair enough. Okay. So, all right, let's take a look at this. Okay, so what are these things here? I don't know enough about these things. These are versions of the Ethereum virtual machine?
That's right. So what we support right now is the two latest ones.
Okay. And
there's not enough. There's not enough to come in.
There's a pseudo opcode or something that specifies which virtual machine is being used. Is that correct?
Yes, and the thing is, there are some opcodes that are not valid in some newer opcodes, for example, that are valid in Petersburg but not in Byzantium, etc. So that's why we need to have these different implementations.
Right. Okay, fair enough. Hey, hold on just 1 second here. Yeah, okay, go ahead. All right. So let's take a look here. Okay. I'm not sure that's the right way to do this. I mean, when we do Python subversions, how are we doing that in external evaluate? How are we specifying the Python subversion? Do you know the answer? Does anybody here know the answer to that?
That's an extra option in the external the start session.
Yes, we only use this because this is what we do with blockchain base as well. But that's a
I see. So with mainnet and so on, specifying.
Right.
Okay, fine. All right, fair enough. Okay. Virtual machine to bytecode. I don't like that name at all. I mean, that
well,
should be.
we didn't either. We didn't either, but we weren't sure what to put.
Well, I mean, it's a string, virtual machine string to bytecode. And by the way, that's not a bytecode. I mean, what the bytecode, I mean, we should say string to byte array or something. Virtual machine string to byte array.
Yeah, well, it could be a string. It could be a list as well, a list of strings.
Yes, fine. But I mean, I think that is, I don't know what to call that. I mean, is that assembly language? Is that, what is that? Let's see. I mean, by the way, some questions on the live stream. Can we convert the bytes to an assembly-like sequence of opcodes to actually read? Yeah, that's what we're talking about right now here. So can we take, for instance, a compiled function and send it to the blockchain? Yeah, well, yes, that is, we're not quite science fiction, but that's, where we're ultimately hoping to go with this. Generating JVM or LLVM bytecode with these functions. Right. So that is an interesting question, is whether the LLVM virtual machine, we want something general enough that we can actually give a piece of LLVM code to this virtual machine function and have it, execute LLVM. And I guess also the JVM we could also do that with. I mean, I guess we have, JVM running within our infrastructure. I don't know. That's an interesting question. What the state of the JVM would look like. Does anybody here know that? Probably the wrong group to discuss this.
No, I'm not sure.
It'll be a good question to ask Todd Gailey. He may know that. Mm-hmm. Okay. So in this case, all right. Well, that's cool. Program that leaves in the stack the world population growth from 1950 to 2019. How come there's so few bytes? I don't understand why that bytecode is so little data. What happened to all those people from 1950 to 2019? I don't understand this.
Luis, can you expand?
Yes, what this does is it pushes the number of the population to the stack in 1950, then pushes the number from 2019, and then subtracts those two numbers. And that's the code that will do those operations. Okay,
I understand. So it's like using an old HP calculator where push, what does the 10 mean here?
10 bytes.
Okay, fine. So that's literally looks very much like the thing we saw with Bitcoin here, where we have, op hash 160, blah, 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 right? So that's like...
Yes, those are the opcodes.
Okay. All right. Okay, so let's take a look here then. Fair enough. I mean, I think this is wrong that it's giving, it should be a byte array down here, but okay.
Yeah,
converting this.
Are we agreeing on a name for these functions?
Not yet.
Not yet, right? Mm-hmm.
Okay, so converting that to opcodes. Okay, so there's the program. So what is this? So this is
some bytecode that this is a very simple Solidity program that was compiled using this remix, and so that we can use this as an example. So if you put all this code in here, that's all the opcodes you get using our function.
Okay.
This third one is a more complex thing. We're just
okay, but so wait a minute. How do I run this code? I mean, given the state of the machine at the initial state of the machine, I want to see the steps associated with running this code.
Yes, that's coming further down.
Okay.
These are only like the support functions. That's what we want to show you next.
Okay.
This last one, the virtual machine code template, is just that it seems useful to have a function that can, there's some contracts that are very usual, so we can give the code for them.
Right. Mm-hmm. So there'd be an ERC, 721 or whatever it is with these parameters. And that's like a curated collection of code templates.
Right, that's the idea with this. But right now we have only 2 or 3.
But how does it know this? I see. This is you put the type in that association. Okay.
Mm-hmm.
Okay. I don't quite understand this. I mean, what's this input type, output type, opcodes? What is that?
That means the virtual machine code template is having its code specified as opcode instead of bytecode, that you want the code generated by it to come out also as opcodes.
All right. So this is a name. So your term opcode is a name for this kind of string-like, this sort of human-readable string.
Yeah, the human-readable strings are usually called opcodes in Ethereum.
But opcode is the name for a single one of these. That's an opcode. Push one is an opcode, right?
Yes.
So this is more like an opcode string.
An opcode list.
Okay. Okay, fine. Okay.
This is a part where you get to evaluate the virtual machines.
Okay, so let's take this. I just want to see what it looks like. Okay, instance. Okay, so that's
that's to differentiate. Yes, that's to differentiate between instances, the parameters from your local node, and blockchain state will be the parameters from the overall blockchain. Probably the names could be changed. I'm not sure about that.
Okay, so this is running inside your local instance of the virtual machine. And these are I don't quite understand this. I mean, this is related to this.
So you're since you have not specified any special properties, you're starting with an empty blockchain.
Mm-hmm. Empty blockchain altogether. I mean, this isn't something living on the, Ethereum mainnet blockchain or something.
No, empty altogether.
Okay.
So the idea with this is, if you don't specify anything, just for example Ethereum, then we should be able to initialize this session with the minimum amount of variables set up, so that you can start playing around like in a sort of sandbox or whatever.
Right, but don't you want to be able to initialize the blockchain as well as initializing this particular virtual machine then? You're saying that there's a way of initializing, a way of starting a blockchain from nothing, right? And that seems like a separate problem than starting this individual instance of the virtual machine from nothing.
Yeah, maybe we could add that. In the example below, it shows how you could start a blockchain with some specified characteristics.
So this thing here has, what is this? This is putting a contract as the only thing that's on that blockchain. The genesis block of that blockchain is this contract. Is that right?
Exactly.
and this create contract. So this is using the address of Warsaw contract, blah, and then it says, okay, use this create contract, which is an example we generated above, which will just create a contract. It's just a very simple example.
You know, if we can get this cleaned up, this is really a terrific thing for the MOOC that, you know, the blockchain MOOC that we're building. Yep. Have you been talking to Johan and so on? I mean, to John about this?
We mentioned, yes, we talked about this a while ago.
I think this is really important for that. I mean, this will really explain to people, you know, at the lowest level. I mean, I don't know how they're organizing their MOOC, but you know, somewhere in it, if people want to understand lower level.
At some point, people which would be more inclined for technical details would like to see how this works. Yes,
especially the step-by-step solutions.
What do you mean by, you mean what, when we can run separate steps? Okay, you're about to show me this. Here we go. Oh my God, it's complicated.
Yeah, it is.
Okay, so this is running, so this is an execution trace of this machine, basically. Is that correct?
Yes.
Okay.
Since no gas limit or way was specified, it's assumed that it's working with infinity, so you can sandbox.
What is that? So that's a special pseudo instruction.
Yes, just creating a transaction costs gas.
Okay, so, gosh. Okay, so the state of the machine. Where do I see that?
It's the result from the first virtual machine evaluate.
Where is that now? That's this result here? No.
No, you have to scroll down a bit. Yeah, there.
I see. So there's a blockchain state, and somewhere here there is a
instance.
The instance will be the state of that particular machine. That's right.
Okay.
So that holds the variables that carry all the state, the stack, etc. Stack memory, etc.
So in a more general case, if we were doing, you know, the Java virtual machine or something, we would want probably in this association, we would want something that says machine state, and then we want something that says global state. Is that right? And global state in this case would be the state of the blockchain.
Right.
In the case of
right.
Okay. Let's maybe take a look. Yeah, but by the way, how are we actually running? I mean, the actual implementation of the Ethereum virtual machine, is it our own code or is it some standard, you know, underlying C code or something?
No, it's on code.
How complicated is it?
Like 5,000 lines at least.
Oh, for goodness sake. Okay. How do we know it's right?
Well, I have been running tests, and up to now, most have come up correct.
But so the reference implementation of the Ethereum virtual machine, what is it? Is it C code?
Yeah, I think that's in the GitHub repository for the virtual machine. In C.
And why aren't we just running that C code? why don't we just, make a WSTP connection to a program that's just running that C code, so that we know it's, whatever bugs it has are the same bugs that the, standard implementation of the EVM has.
I think sorry, I was going to say that I think the original language is Go for the EVM, but there are implementations like in 6 or 7 different languages.
Okay, but I mean, whatever it is, we should be able to run that program in our system. I mean, for all the different blockchains, we should be able to run their virtual machine program without, I mean, we shouldn't try to rewrite all these virtual machine programs. It's a huge amount of work. I mean, it's interesting, I suppose. I'd be interested to see that code. Let me see. Is that what you just sent me? I mean, that.
Yes, that should be part of all these .ems.
So it's like Petersburg.m. Is that an implementation of the Petersburg?
Yes, that's the Petersburg version.
My God. Okay. I mean, it's magnificent, but I don't understand why we're doing this. I mean, why aren't we just calling some standard reference implementation of this virtual machine? What did I miss here? Is there some reason why we need this in top-level code?
I'm not sure. I guess it's just how it got done from the beginning.
I think this is the wrong thing. I mean, I think it's magnificent. It's interesting. It's an interesting example of code, but I think it's the wrong thing, because I think we can't, this is completely non-scalable. Right? I mean, it's very impressive, and that it works is even more impressive. My gosh. Well, okay. I mean, to me, what I wanted us to concentrate on was the top-level design here, because that's what, I would have thought we should just call, you just feed an opcode string into some, I assume that these C implementations or whatever they are, Go implementations, take the byte string or byte array and just grind, they can do one step and then give the result, presumably. Yes, I mean, should I look at the GitHub repo for
I don't think so. What happens is that the client usually comes with the virtual machine already incorporated, and the node just runs all the transactions that come to it after synchronizing.
Okay, what's this? Okay. Okay, I understand. Right. Yeah, Carl on our live stream is pointing out that there's a Java version of the EVM where we could just use JLink to call it. And people are also saying that it would be cool to publish the Wolfram Language implementation on GitHub, which we should probably do, because it's not that's an interesting thing. Okay, but the main thing we want to concentrate on is kind of what it looks like what we were talking about before. What is the basic structure of, I think we had a virtual machine, virtual machine execute or something that takes the machine spec and then takes the state and returns a new state.
Yes, we used evaluate because of the already existing object.
No, that's good.
Evaluate.
Yeah, that's good. I mean, but okay, so that runs a complete program. Yeah, I don't really know what you're saying in that case would be, program. That returns output typically. Now, these programs on the blockchain, what do they do? What is their output? Or are they changing, or they have some side effects on the global state? What's the deal with that?
Yes, some contracts can change the state of the blockchain. Others just are read-only.
Mm-hmm. But when they read, when the program finishes, does it have a return value?
Not always. It has a return value only when requested by the operation, by some operations.
Mm-hmm. Okay. Okay, but so
but that return value is something included in the specification of the instance. So that's why the idea was to return the full state. So that's part of the state also, this return value.
Okay, so you're saying machine spec program state, and then it returns the state. And the state in general could contain a machine state and a global state. Is that right?
The return net values could be in the machine state.
Well, wait a minute. I mean, the machine state could have a program counter that moves, for example. Right. So I mean, this would be either evaluate one step or evaluate until the program terminates. Is that right?
Yes.
Or generate an execution trace. So one could imagine something where what we're doing is we're saying, given virtual machine evaluate, we're saying ask for a particular property, which could be the final state, the number of steps it takes to terminate, or a variety of other things. Right? I mean, I think that's is that right? I mean, that would be the that would be the type of thing we would expect there. Yes, does that make sense?
But if we are calling another implementations, I don't know if they will return all the values one might expect.
Fine, that's a reason to use ours in those cases. But I mean, I think we can have a method option that says which implementation to use. So, I mean, by way of analogy, let's look at, I think I'd shown this before. Let's see. Yeah. These things as incredibly minimal virtual machines, register machines. Okay. So their programs look like this: increment register 1, decrement register 2, if it, skip on 0, I think that is, to instruction 1, etc. So, in this case, if we had a register machine here, we would have essentially machine state goes to register 1, goes to blah, blah, blah. We might have something called registers that just is a list of, R1, R2. Does that make sense? And this has no global state. And then these things here, then the program would be typically something like, so program is presumably always, program is a list of opcodes, basically. It's not really opcodes. I mean, opcode is the name for, like you say, the x86 instruction set has this set of opcodes. The opcode is a thing that says like push or add or mult or something like this. I don't know what the name for the whole line is. Does anybody know? Is there a standard name for the whole kind of, the whole line of the program, so to speak, as opposed to just the actual opcode? In other words, every mult is an instance of a single opcode. It's not that every instance of mult is something. I don't know what its name is, but the mult itself is the thing that's called the opcode, I think.
Well, besides calling that a statement, I'm not sure.
What?
A statement or comment, you can call this opcode plus the arguments. That's what you're referring, right?
Yes. What were you calling it? A statement or what?
Or a comment for this program. So everything is a script, let's say, right?
Okay, fair enough. Okay, so there's a program is a list of commands, each specified by an opcode. Is that a fair statement? So, I mean, what we could then have is something in principle where we say, opcode arrow mult or something. And then arguments arrow whatever they are, perhaps. Alternatively, like we've done for web execute, we could conceivably imagine a shorthand like this. So okay, so then let's look at how that corresponds to what you've got over here. So this is saying, so first of all, we've got what is the machine spec? So the machine spec here is the theory in Petersburg. Yes? Now, then we've got machine state is this thing here. So gas available we can think of as being the value of what's in a register. Is that a true statement? I mean, is the gas available as like a register, like the content of a register? See what I'm asking?
Yeah, that's something that it's changing while it's evaluating the comments, right?
Well, like the contents of register. So is the stack, okay, so the memory, how is this memory represented?
It's an association of positions in the memory and the value.
Okay, so we can see that happened here. Okay, so it's a zero origin array where that's the pointer value. Is that correct? And this is the content. Now the content, why isn't the content an integer here? Is this content in hex or what? Yes.
Yes, it's hex.
But for our purposes, shouldn't it just be an integer that you might choose to print out in hex? In other words, I would expect that what this would be is that the memory I mean, it's a nuisance that it's a zero origin array, but given that it is, I would just expect an integer there.
Now that can be changed.
Right. I mean, we could also, for efficiency, we could have, but I don't know whether this really matters for this, we could have a memory byte array, which is just the compressed version of this, because each one of those is a byte, isn't it? Each one of the right-hand sides is a byte.
Yeah,
yes.
What worries me is that it should be a sparse array at any case, because it could grow. So you can refer to far parts of memory.
I see. Okay. Okay, fine. So that's probably a bad idea. So an association is probably the right idea, because in this particular case, the memory that's being used is contiguous, yeah, but it's not always true.
Right.
Okay. What's this origin and caller and so on?
Origin is the original address that created the transaction, and since you can have contracts that call other contracts and so on, each time you make a new call, the caller changes, but the origin remains the same.
What is a call?
A call is when you request another contract to be executed. So
it's the analog of a subroutine call.
Yeah, it's like a subroutine.
Yes.
Okay, so effectively then, I'm a little confused here. You're saying you're then getting that, in this particular example, you're getting that subroutine from the global supply of everything, which is the blockchain, correct? Whereas in a let's say it was a Java program, that would be some separate piece of code that you have to pull in from somewhere. And it's like, if I define f of x blank colon equals whatever, I could refer to that piece of code as f, right? And that's the kind of thing you mean here. But because there happens to be in the blockchain world, there happens to be a global source of everything, namely the blockchain, you just have to give the address on the blockchain for that.
Yes, in the Ethereum case, yes.
Okay. But more generally, we need a way, I mean, my gosh, we're going to have linkers and loaders and everything, all the usual stuff at some level, because, in a sense, what you want to be able to do is within this one virtual machine program, you want to be able to reference other virtual machine programs. You want to transfer control to a different virtual machine program. I mean, that's going to get very complicated and maybe not something we should be supporting. But here, as soon as you call another contract, you're running code that you're not seeing here, right? So you think you've got a virtual machine that is running this piece of code, but actually it calls some other part of the blockchain and runs another piece of code, correct?
Right, but in this implementation, of course, the trace can go through all the statements because everything is here. But yes, well, that would be the advantage of having our own implementation. So.
Right, I agree. That's an advantage. I agree. That's a good thing. Okay, all right. So these are essentially special registers: the gas available, gas spent, and so on. Is that true? I mean, and the stack. What on earth is that stack? What is that?
That's all the opcodes take their arguments from the stack, not from the memory.
Okay, but
so that's the regular stack of where the opcodes operate. So the push
I understand, but so it just so happens that giant big num was just pushed to the stack. Is that a single operand value?
Yes, in this case,
it was a small string.
Yes, in this case, the remaining object from the stack is that huge number.
Okay. But in general, okay, so in general, there'd just be a stack which is, by the way, Tom is implementing this new data structure thing that allows mutable data structures. And you might point out to him, could somebody mention to him stacks? I don't know if he has that on his list. He probably does have it on his list, but it'd be nice if his data structure system, was compatible with whatever stacks, computation stuff exists here.
I'll relay the information to him.
Okay. So someone on our live stream was saying it'd be nice if the push opcode was generalized so you could just pass an integer. So I mean, it's polymorphism for for low-level opcodes is basically what's being asked for. And I think that that's a level of kind of symbolic representation that we haven't quite got to here. I mean, that's certainly something that, I mean, that requires compilation and code analysis to go from the generic push-up code to the particular one that you should be using for the data structure that actually occurs at that stage in this particular program. Yeah, someone's pointing out it might be time for sparse byte array. I don't quite think we're ready for that yet. I don't think the I agree that it would be a gosh, that's an interesting. I mean, in you know, if you take a core dump or something and you're analyzing it, I can see that there's some value to having a sparse byte array for core dump analysis, but I think that's a future adventure. Carl is pointing out that state space models and the things that we have in the microcontroller kit are in some sense also virtual machines. And Brian is asking, how would you validate a transaction before calling its code? So, I mean, don't we have a, no, we have a, you can set up a blockchain transaction, right? And then you simply sign the transaction and make it happen, right? I mean, that's not a, what am I trying to say? But validating, it's a question of what the validation, you know, what does it mean to validate a transaction? What properties do you want to be true of a given transaction? That's the interesting thing, where you're essentially defining a computational contract for what should be true about that transaction. And that is indeed what we would like to be able to do with these virtual machine simulations, is be able to say, given that we want this property, is that true for this particular contract? And I mean, for that, ultimately, so I mean, you know, an example of a stretch question is, can we make one of these things symbolic? That is it conceivable that we could say the input to a virtual machine is just X, and that we could get out here a piece of code, or for that matter, an essentially mathematical expression that represents the operation of that virtual machine on input called X? Did that make any sense? Like, what happens when, you know, if I turn one of those literal operands into a symbolic operand, can I have some symbolic representation of what's going on? Which is what I thought, you know, because that's where, if we're going to do validation and theorem proving, that's what we have to operate on. Right? And presumably that, like that Isabel implementation of the EVM, presumably is something which has some kind of symbolic representation on which a theorem prover can run. Did I lose everybody, or did everybody kind of reaction to that? Hello, anybody there? Oops.
We're here. I think we are just processing what you just said.
Okay, but I mean, I think, yeah, we're pretty much out of time for this particular meeting, but look, I think there's several things we really need to look at. We really need to look at what's involved in simply hooking up existing, you know, virtual machine implementations. What's involved, you know, kind of cleaning up this interface here. I think it's clearly useful. I mean, for example, I would have thought that some of these earlier things that you had here, like virtual machine to bytecode, I mean, I'm kind of wondering whether those are import-export functions, whether, you know, you're simply taking the symbolic representation and saying export it as a such and such string.
It's much, I think, an encoder than exporting, but yes.
Well, okay, fair enough. I mean, this is basically, I mean, basically what you're talking about here is something like, you know, it's basically virtual machine encode or compile, I don't know, virtual machine encode, virtual machine decode, something like that. I don't know what decode does. I mean, I think that's supposed to go from the machine code to some decompiled form.
That will go to the list of statements. So,
yeah, but which we really would like to be symbolic, not just a list of strings. I mean, in a perfect world, what we would have is something that says, opcode, push or something. I don't know. Well, we could call it virtual machine. Let's just for shortness say VM operation, and then it's push, and then it's the operands. And the goal here is to make it be the case that we could say, something like this, and we could say literally X, Y, 6. And that then we would be able to have something which says, I don't know what it is, VM resolve or something, which turns that into 6XY. In the case where we can do that. Because there are cases where, and that's obviously something we can't get from, that's something we have to implement for ourselves. We can't, that's a reason to have a top-level Wolfram language implementation, because it's capable of being symbolic. Right? And presumably the code you've already got there could perfectly well be fed symbolic inputs. I mean, if I take a look at that code,
well, it already has the infinity, for example.
Yes. I mean, so that's an exciting thing that becomes possible with this code. I mean, that's I don't know whether it's been fully, symbolic hardened. But
we could clean that up enough so that it could work symbolically. That would be nice.
Right. And again, what I would expect is that the program is represented by some sequence of symbolic operations, and that then there are rules that are, feedable to the theorem prover that say things like a push and a pop, is equivalent to the identity or something. Am I making sense? And then, that becomes essentially the definition of the operation of the machine. And again, I would assume that that's what that Isabelle version has in it, is a set of essentially assertions about the operation of the machine from which you can prove theorems about the machine. That's what I would anticipate.
Right. Anyway, I think we will need this form of full string, because that's the way the people writes the programs, and so we should be able to.
Oh yeah, no. I mean, listen. Clearly, what we need to be able to do is you find some random byte array on the Ethereum blockchain, or for that matter, the Bitcoin blockchain. You say, what is this? And you say, here's the symbolic representation of it, and let me run it on some sample inputs. Okay, great. Here's what the execution trace looks like. Or alternatively, let me run it on symbolic inputs and see, oh yes, this thing, I mean, it may not resolve. It may be something where what the thing is doing is computing 3 random numbers and, sending your fortune to, random people on the blockchain, chosen by those random numbers, maybe. I don't know. So, by the way, a point being made by Brian on the live stream is that one would need to name transactions, and one would need to have a notion of symbolic code blocks. So, for example, if you say, at this moment we call the thing at address F on the blockchain. Let me not use F, S. So we're out of the hexadecimal zone. Address U on the blockchain. Then address U would be a symbolic function that, we say, and then it's basically just U of whatever arguments it is, represents the, and that's not resolved yet. And so, for example, when we have a theorem proving, it could be that with our predicate logic theorem prover, that it could be, well, I don't care what U is, because, what appears is U appears in a way that's factorable out from the operations and so on. But anyway, look, I mean, I think the thing we need to do is, you've got a good start on the overall framework. I think the details of the implementation, I think a huge amount of work was spent here on getting a top-level Wolfram Language implementation of EVM. I think if we can make it symbolic, it's super cool and very useful. I think, though, that the original brief of this project could have been executed just with, outside implementations of these blockchains, and I suggest that we get a pipeline for how to do that. Then I suggest that we should do this as an experiment for register machines and Turing machines and things like that, to just check that the formalism we have actually works for those. And they're going to be a lot simpler. They don't have gas prices and things in them. They just have values of registers or the state of the tape. And the state of the tape is obviously the analog of what you've got with memory and memory locations. And notice that the way we're representing, in the Turing machine function, we're representing the tape, and it's a little bit tricky because in that case it's a doubly infinite tape, which probably in some world could be represented by its the pair of location with 0 in the middle, from minus infinity to infinity. We're choosing to represent it as a one origin, array that doesn't have extensibility on the left, so to speak. But I think, that would be using that to represent what you're calling memory here is reasonable. I think that we've probably got other simple models where, a trivial stack machine should also be representable with one of these virtual machines things. So, I think we've got 3 types of virtual machines that we care about. We've got the very idealized virtual machines like register machines, Turing machines, and so on. We've got the very kind of practical everyday like LLVM, like JVM, those kinds of things, where presumably their state, I don't know how many of those things run in enough of a sandbox that there aren't external I/O interrupts and things like that that have to be represented. And then finally, we've got this sort of hybrid case of the blockchain virtual machines, which are kind of a little bit of a hybrid between these very low-level theoretical things and these very high-level kind of fully functional LLVM, JVM type things. So, all of these, we want to be part of what we represent as a virtual machine. Now, of course, there's an even more ambitious thing, which we're not doing yet, but one day we might, which is to take an actual VM of the kind that we deliver Wolfram Engine in an actual I don't remember the kind of the brand names of the VMs, but an actual official complete VM where its only interaction with the outside world is being poked through its various network connections and so on. It would be nice to get our formalism here to have the possibility that that VM could essentially represent a remote kernel. Did that make sense, or did I just freak everybody out? Everybody is totally freaked out.
Oh, it makes sense, but yeah.
At least with the virtual machine for Wolfram Engine, yes.
Yeah, a virtual machine for Wolfram Engine is a. That's a. I guess. See, the difference is that, when you have a Wolfram Language session, there is implicitly a state of the machine. There's a state of the session. We don't usually explicitly show you that because it's like you're defining variables and it's like, okay, they go off and they're defined. But we could imagine, actually, it would be quite useful, and probably we already have this formalism for some of our sandboxes. I bet we do, of something which just represents this is the whole state of the Wolfram Engine virtual machine, right? So in other words, you've defined, so what is the state of the virtual machine? The state of that virtual machine is basically the values of a bunch of variables.
Well, that's almost when we do dump of asterisks of all the context.
Yeah, that's right. That's the. But in a purer version of that, it's just. The thing that's awkward is that you might hope that the Wolfram Engine is sort of an immutable thing, and that then it's operating on this state that simply is an association. So I mean, you know, essentially we've got the, you know, this is the Wolfram engine VM. And what we would have here is something where the state is, you know, X goes to, well, probably it has to be a string, but the, you know, it might be, you know, symbol values. And it's things like, you know, X goes to whatever it goes to, et cetera, et cetera, et cetera. And so what we could imagine here is then just running, you know, it's a little bit funky because at each point, the Wolfram engine runs to a fixed point. So it takes the state of the world, and whatever that state is, it iterates that state until it reaches a fixed point. And the way that normally in a session, the way you're going to the next fixed point is you're adding input and saying, okay, go take this to a fixed point. And I suppose the same is true with even the EVM, right? That you're starting off from some state and it's just going to run until it gets to a fixed point. That true? Where it runs until it has executed the program, it's finished, so to speak.
Yes.
And then the way it gets activated again is on the blockchain. The way it gets activated again is somebody puts some new thing onto the blockchain, which might potentially recall that piece of code. Right? So in other words, like one of our sessions where somebody is putting new input into the Wolfram engine, and then that's, you know, sort of iterating and getting results. So similarly, what you're looking at here is the thing. Yeah, okay. Well, this is interesting. I mean, I think we've got some distance to go. I think, I mean, I guess you guys understand the vision for what this virtual machine function, you know, which again, I see what people will do as being things like this, you know, define a register machine. You know, we've got a register machine definition now, and we might have multiple kinds of register machines. And now, you know, there's the toy problem of prove a theorem about the register machine. Then the next level up is, given the EVM, you know, prove a theorem about that. Or in some of these other things, I mean, I could imagine, you know, if we had a very efficient implementation of this, this is a perfectly sandbox. I mean, we would love it if a bunch of other languages had a virtual machine that was encapsulated like this, because then we could run them, you know, we could safely run them. They have no side effects. All the state is represented in the actual association that comes out of the execution of the virtual machine. All right, well, to be continued. I think this was a kind of a kickoff discussion of the virtual machine world, but maybe you guys can have a think about this and see what, you know, see what some quick paths to implementing some of this stuff are. Does that sound reasonable? Yeah, go ahead.
Yes, and so also you suggest to change to this machine state and global state for names so they can be generalized, right?
I think I'm suggesting that, yes, but I'm not going through the full naming sequence because I think that these, you know, this type of stuff, I kind of think that, you see, for example, when you say virtual machine to bytecode, I mean, like Turing machines have a, you know, weird specification, you know, 1S, you know, whatever it is, I don't know. You know, there's a compact representation of Turing machines that's often used, and I think that is something we would probably want to support, just like we have a. I mean, you know, actually, the other case that we should support is finite state machines. I mean, that's the, you know, where essentially it's a regular expression that's being given or a graph, where that starts from a regex or a graph, and where essentially we've got a, you know, virtual machine evaluate. Again, this all requires thought, and you know, we need to have a formalism that will work, you know, for a finite state machine where you've just got, and again, I'm not completely sure about the way that evolves to fixed points and all those kinds of things. Anyway, very interesting stuff. This is a beginning. Have a think. Let's talk about it again in a little while. Sound reasonable?
Yes, makes sense.
Okay.
Okay, thanks.
Thank you all.
Okay.
And thanks to folks on the live stream. and see you all later.